class on hardware security. So, we shall be continuing our studies on power attacks and in the form of side channel analysis. In particular, today we shall be studying a different perspective on side channel analysis, which is essentially to test whether a given crypto system is vulnerable to side channel attacks. So, in this context, right, we shall be studying two approaches, or which are well established, which are called as common criteria and Phipps test. And we shall be trying to look at the merits and demerits of both, essentially trying to understand what they stand for. We shall be trying to look into some parameters of both CC as well as Phipps. For example, as they are abbreviated as signal to noise ratio, or SNR, as we have seen. There is another important parameter which is called as NICV. We shall be trying to look into a test approach which is commonly called as the test vector leakage assessment, or TVLA. And we shall be trying to see the link between TVLA and NICV. So, our objective will be trying to develop a homogeneous test strategy, trying to kind of combine both CC as well as Phipps and trying to get the best of both. So, we shall be trying to look into few interrelationships like within TVLA and NICV, between SNR and SR, and finally conclude with some experimental case studies to see how we can apply this test strategy. So, to start with, we all know that we have got these cryptographic implementations, and essentially the story is that if the cryptographic algorithm is nicely developed, then the revelation of the plain text and the output ciphertext does not give information about the key. So, therefore, if there is an adversary who is observing classically the input as well as the output, then we are kind of safe. I mean, our cryptographic algorithms are quite sound to prevent, or at least reasonably be resisting against such kind of adversaries. But then, right, as we have been studying, that there are some other things, for example, what are called as side channels, like essentially there could be several forms of side channels. There could be power, there could be electromagnetics, there could be timing. So, the question is, right, how do we really, like under such kind of, I would say, stronger adversaries who are equipped with like instrumentations to do these kind of attacks. I mean, the scenario is that most of our designs are vulnerable. So, therefore, right, we need to develop an approach to know how our methodologies are sound against side channel attacks. So, there are different styles which has been proposed in literature. Two of the most common styles, and the first that I will start with is what is called as the common criteria certification, which is an example of evaluation style testing. So, in this particular approach, this was originally is also standardized in ISO in the 15408. It defines a common framework for evaluating cryptographic implementations using a standard set of predefined assurance levels. So, therefore, right, what do we do here is essentially depicted by this flow chart. For example, what we do is if I want to adopt an evaluation style testing, then the attacker performs different side channel attacks. So, therefore, as we have seen that there are different forms of side channel attacks, the adversary kind of tries to, or the evaluator basically tries to apply these various attack techniques one by one on the target cryptographic implementation. So, of course, right, when you are applying a specific attack, as we have seen, like when we are doing say DPA, or when we are doing template attacks, right, or if we are doing mutual information based attacks, one thing which is very important is the leakage model. So, therefore, in this particular testing styles, right, we essentially assume that the adversary has an idea, or the evaluator has an idea about the underlying leakage model. And also he makes a target, like if you remember, right, we were targeting the output of the S box or the input of the S box. So, there is a specific target on which you are attacking. Okay. Now, note that in a given cryptographic implementation, right, there can be several targets. Okay. So, therefore, right, I mean, what is important is also to know, like essentially we are assuming here that the adversary also has got some kind of knowledge about the target, which is essentially better suited for doing an attack, because if you are probably making an attack on a wrong target, and then you can actually come to wrong conclusions. Okay. So, therefore, it is important that you make kind of like an exhaustive, or at least a reasonable exploration on various targets, and you are confident about your final conclusion. And at the same time, right, I mean, this is a non-analytical method to estimate the success rate, which means you are doing the attack and you are measuring the actual success rate from real life experiments. And of course, that means that it depends on the lab expertise. It depends upon how much level of expertise you have on doing side channel attacks. And therefore, this is a pretty much time consuming and cumbersome approach. And although it can quantify vulnerability because it is actually doing an attack, but this is a non-analytic approach. So, if we now go through this flow chart and just quickly see how this testing approach works, it is as follows. So, you probably would like, as an evaluator, develop capture several side channel traces. You will make an assumption on the leakage model, and then you will be doing the attack, the crypto algorithm from the output or the input, like you will be processing the plain text or the ciphertext, and then you will be starting your attack procedure. Now what you will do is that you will be starting your attack procedure, you will be continuing with your attack, and if your attack is not successful, then you essentially again try the attack. So, basically you try repeatedly to do the attacks, and therefore you are kind of increment a success counter if your attack works correctly. So, finally, right, you based upon the number of times, say if you are trying say 5,000 times an attack, and if you for example are able to do an attack say 4,000 times, then from this statistic, right, or from these values, you try to estimate the success rate and also the guessing entropy, as we have seen. So, now given like the success rate and the guessing entropy, you basically make a conclusion that whether depending upon depending upon the the assurance level that you want to kind of implement or deploy your device. For example, it may be a very highly sensitive application, it may be not so highly sensitive application. So, depending upon your application scenario, you make a decision whether this attack potential is acceptable or not. Okay. If it is acceptable, then you say that it is secure, okay, under that context. Otherwise, you say that it is not secure, which means it is vulnerable with so many amount of traces. So, as you can see that the entire approach is non-analytical. It is basically based upon that you are doing an attack, and based on the performance of your attack, you are making a conclusion. Okay. So, therefore, if you really want to adopt this evaluation style for your laboratory, then you need to also have a reasonable amount of expertise to do these attacks. So, there are different metrics which has been proposed to in this evaluation style. Two of the most common ones are what are called as SNR, as we have seen, as signal to noise ratio, and the other one is what is called as NICV, or what stands for the normalized interclass variance. Okay. So, let us try to define this in our context. Okay. So, we will make, in order to formalize or define these notations, we will basically start with certain a definition of our leakage model. Okay. So, we basically again have got an intermediate state. So, let us denote it as x, and suppose k is a single is the corresponding key byte, okay, or it could be a keyword also. Okay. So, without loss of generality, you can tell it as byte. Okay. So, now what you do is you also denote the corresponding leakage. So, the leakage now depends upon this intermediate value, which is x, and also on the secret key. Okay. So, therefore, what I mean is that the leakage will depend upon either you can process the attack from the input size, which means from the plain text size, or from the ciphertext size. Okay. So, again, without loss of generality, let me assume that you are doing the attack now from the plain text size, and suppose the plain text is x. Okay. You make a guess for the key byte, or the key byte is say k when you are actually doing the attack, and therefore, this x gets mixed with this secret key, gets processed by say something like an S box or so, and then you get a target. Okay. So, therefore, the leakage is basically a function of x and k, and that is denoted as this function Lx comma k, and is denoted by this random variable capital L. So, again we can make, without loss of generality, an assumption that the mean of this is 0 and the variance of this L is equal to E of L square, which is equal to 1. Okay. So, we can essentially define a corresponding leakage such that these parameters are satisfied without loss of generality. So, now what we do is we note that the corresponding, like this is the actual, I would say, the deterministic part of the leakage, but this gets kind of contaminated with the Gaussian noise, okay, as we have seen previously. So, therefore, right, the actual observed leakage, which you see is denoted here as y, and that is nothing but kind of the superimposition of the deterministic part, which is denoted by L multiplied with the scaling coefficient, say epsilon, plus the noise, which is nothing but a Gaussian whose mean is assumed to be 0, again without loss of generality, and the variance is denoted as sigma square. So, now we have got this y as your output observed leakage. Okay. So, now we would like to define our signal to noise ratio. So, remember, right, we defined our signal to noise ratio. It is kind of again like a kind of again redefining that, but you can observe that essentially they are the same. So, the numerator is exactly the same. For example, it is the variance of the expectation of y given x. Okay. So, this, as I said in the previous class, is the signal component of your leakage consumption, whereas the denominator stands for the noise. Okay. So, therefore, here you can see that it is the variance of expectation of y given x, that means given the corresponding input class, you are basically trying to define the corresponding leakage. So, essentially if the variance is high, then that means you can easily distinguish the x values, and therefore your attack works, and therefore this contributes to the signal component of your side channel attack. On the other hand, right, I mean, this is the noise component. Okay. This I will kind of clarify very soon, but you can right now note that it is very easy to remember. It is the variance of expectation of y given x divided by the expectation of variance of y given x. So, this is a kind of convenient formula to apply to estimate the signal to noise ratio. When you are estimating the signal, the other parameter, which is called as NICV, or the normalized interclass variance, it is kind of similar to the SNR, except that the denominator has been replaced from expectation of variance of y given x to the variance of only y. Okay. So, you can see that I have just replaced this from variance of our expectation of variance of y given x to only the variance of y. So, note that if you want to estimate this parameter, that means if you want to estimate the denominator, then you need to kind of have a knowledge about x, you need to kind of estimate x, because this is conditioned on x. Okay. And if you want to kind of have a knowledge about x, right, you also need to know the subpart or the secret key. Okay. So, therefore, for SNR estimation, you need to have a knowledge about the secret key, whereas here when you are measuring the variance of y, you are basically doing it only on the output leakage, and therefore you did not need have any knowledge about the key. Okay. So, often this NICV is very useful. It is used to find out the point of interest on the side channel trace, like essentially you can kind of pretty much apply the NICV to know like what are the sequence of operations in your implementation, like you are doing the mix column, then shift row and add round key and so on. So, now let us try to kind of look into these metrics in a little bit more details, right, and again we will start, we will adopt this. So, we will throughout our discussion we will be assuming this leakage model, which is y equal to epsilon L plus n, and now I want to calculate the numerator part, which is the variance of expectation of y given x. Okay. So, let us recapitulate this a little bit. I mean, what this means, like this is essentially nothing but the conditional expectation. Okay. So, that means if I say you expectation of y given x equal to small x, okay, that means in this particular leakage I am fixing the value of x, okay, and then I am calculating the expectation. Okay. So, note that since it is plus, I can apply the expectation on this plus the expectation on the noise component, and the expectation of noise component is 0. So, therefore, this does not matter. Okay. So, if you remember, right, noise is a Gaussian, which is essentially 0 comma sigma square, and therefore, the expectation of noise will be 0. So, this component will not bother us. So, the other component is where when you are fixing L, right, then L takes a specific value, the deterministic part gets fixed because you are fixing this input x. Okay. The moment you are fixing x, the leakage gets fixed. Okay, and the leakage gets determined by x as well as k, because k is your underlying secret on which you are doing the computation. So, therefore, right, if I take the expectation, right, then the expectation is essentially nothing but epsilon L. Okay. And now, what is Ey given x, which is the conditional expectation? It is nothing but note that this is a value. This is when you are saying, when you are fixing a value for the condition, then expectation of y given x equal to small x is a value. Okay. But when you are talking about expectation of y given x, where x is a random variable, then this is also a random variable. Okay. And actually expectation of y given x is a random variable and is a function of x. Okay. So, the way we kind of observe it or see it is that which takes the value of Ey given x equal to small x at x equal to small x. Okay. So, therefore, epsilon or expectation of y given x is nothing but epsilon L. So, I can replace this this value L by the random variable epsilon L. So, now if I want to calculate the variance of this, right, then essentially this is nothing but epsilon square and the variance of L, but as I said that the variance of L was assumed to be 1. So, therefore, right, we get epsilon square. Okay. So, now likewise, right, if I want to calculate the variance of y given x, so this essentially is nothing but the expectation of y minus Ey by x whole square given x. Okay. So, this is just to remember that if you just forget, right, then you know that the variance of y is nothing but the expectation of y minus Ey whole square, right. It is essentially the deviation from the mean, right. So, now we have a conditional variance, we are calculating the conditional variance, and therefore, this is the corresponding adaptation that we do to the formula. And if you kind of simplify this, right, you will get this as epsilon expectation of y square given x minus expectation of y given x whole square. Okay. So, this I just leave to you as an exercise to verify. So, therefore, now what essentially you can observe here is that y is nothing but epsilon L plus n, okay. And as I said that E y given x is nothing but epsilon L. So, therefore, I can substitute epsilon L here, and therefore, write this epsilon L and epsilon L get cancelled, and remember the noise is independent of x. So, therefore, I can just write this as expectation of n square, and therefore, expectation of n square is nothing but sigma square. Why? Now, because the variance of n is sigma square, and variance of n is nothing but E of n square minus E n whole square, and E of n is 0. So, E of n square is also sigma square. So, therefore, the signal to noise ratio, which is the variance of E y given x divided by expectation of variance of y given x, is nothing but epsilon square by sigma square. So, note that now the denominator or probably makes more sense when I say expectation of variance y given x, that is equal to sigma square, which is indeed the variance of noise, right. I mean, if you remember, right, originally we defined the denominator part of the signal to noise ratio was variance of noise, and therefore, right, the expectation of variance y given x indeed correctly computes to give you the variance of noise. Okay. So, this is also kind of to show why this is defined in this way. So, therefore, right, I mean, once we have defined the value of SNR, we are all set to see how NICV can be defined. So, NICV, as I said, is a technique which was designed originally to detect the relevant points of interest in a side channel attack trace. So, the main advantage of NICV is that it is leakage model agnostic, okay, and can be applied with the knowledge of only plain text or ciphertext, and does not need the knowledge of the target implementation or the secret key. Okay. So, now therefore, right, therefore, NICV as I defined was variance of E y given x divided by variance of y, and the numerator is again epsilon square exactly in the same way as we have seen previously, and for the denominator we have got variance of epsilon L plus variance of n. Okay. So, variance of epsilon n plus variance of n, which means, right, variance of epsilon L is essentially nothing but epsilon square, right. Again, remember that variance of L is 1, okay, and variance of n is sigma square. So, you have got epsilon square divided by epsilon square plus sigma square, and if you divide the numerator and the denominator both by sigma square, then you have got 1 divided by epsilon square, then you have got 1 divided by 1 plus 1 by SNR. So, therefore, the NICV gets related with the signal to noise ratio. Okay. So, note that or you should reflect, right, that why for NICV, right, you do not know the key, whereas for estimating the SNR you need to know the key, because when you are estimating the SNR you need to estimate this parameter of sigma square, okay, that is the variance of noise. But how will you know the variance of noise? In order to know the variance of noise, you have to observe the total leakage and from there subtract out the deterministic part. But in order to know what is the deterministic part, you need to know the key, okay, because the key is also playing a role in computing the deterministic part. Therefore, right, you need to know the key. Whereas when you are estimating the NICV, at that point you are just calculating the variance of y. Okay, so you are basically taking both of them together and you are not separating the noise component. Okay, and therefore you need not know the key in this case. Okay, so it is a, in some sense, right, for non-profile attacks this is better, because in a non-profile attack you have no knowledge about the secret key until you are successful in the attack. So, now this brings us, so now after kind of having an overview on the first standard, we are basically we will look into what is called as the fifth certification strategy. So, this is again what is called as the validation or the conformance style testing, okay, as opposed to the evaluation style testing. So, here we assume that the attacker does not know or does not require any knowledge about the leakage model. So, in some sense it is a black box testing. It is kind of robust and it does not depend upon lab expertise, or at least I would say depend less on lab expertise, okay, and it is quite fast and easy to execute. It is a fully analytical method, and the interesting point is that it can only detect the presence of side channel leakage, but it cannot quantify the vulnerability. So, I will stress this point later on with some experiments. So, basically, right, it can only detect that whether there is a side channel leakage vulnerability or not, but it cannot quantify that vulnerability. Okay. So how does it look through? Essentially is depicted again in this flow chart. So again you gather some side channel traces. Okay, remember that the side channel traces can be observed as a black box. So you basically get some black box side channel traces, and then you do a validation. So this validation is based on something which is called as a non-specific test vector leakage assessment test, or non-specific TVLA, which I will be defining very soon. So TVLA basically, right, is essentially nothing but a test strategy which was proposed by NIST, which is sponsored by NIST sponsored workshop at NI8. It is called as NI80 workshop in 2011, and it is one of the most well-known conformance tests. Okay, so the TVLA test basically, or the non-specific TVLA test, just does a pass-fail evaluation. So if it passes, then it tells that the design is secured. If it fails, then it is vulnerable. That's it. It doesn't do any quantification. Okay. So therefore, right, this is a very I would say like an easy test and fast test in that sense. Okay, but at the same time, it has got its own limitations. So this is how. So let us now kind of have a look into what this TVLA test strategy stands for. Okay, so the test vector leakage assessment, or TVLA, essentially is nothing but a direct application of Welch's t-test on side channel leakage traces for detection of vulnerabilities. Okay. So note that, so let us kind of first of all see how the non-specific TVLA works. So in the non-specific TVLA, you basically partition the trace or traces based on public information. Okay. So the public information could be just plain texts. Okay. So the plain text, right, essentially are available without even knowing what is essentially internally done, and therefore it is kind of a black box approach. So what you do is basically you acquire two sets of side channel traces. Depending upon, you know, like in the first set, you basically correspond to a fixed key. Of course, the key is fixed, but you also fix the plain text. Okay, and in the second case, you basically give random plain texts. Okay, and now what you do is basically you calculate this parameter which is called as TVLA X. Okay, and there is a hat over that, and I will explain what it stands for. So in the numerator, you basically kind of find out the mean in both these approaches. Okay, so in one case, so basically like you have this, right, you have two sets of experiments that you are doing. Okay, so in one set of experiment, what you are doing is you have got this encryption algorithm, you are fixing this input x to some constant. Okay, so let me make it x equal to k. Okay, and then you are basically observing the side channel traces. So these side channel traces essentially are going into, say, your group 1 or group A. Okay, and in the other case, you are basically taking the same device. Again, it has got the same key internally. So let me write as x equal to c, so that we don't get confused with the key part. Okay, and in this case, we basically vary x at random. So this x is basically chosen from its own input set and given at random. Again, you basically get the power traces. This goes into your group 2, okay, or G2. So now what we do is we basically observe the mean in this case, the mu1, the corresponding sigma 1 square in this particular group, and also mu2 and sigma 2 squared. So mu1 and sigma 1 square are nothing but the mean and the vector, and mean and the variances. And we also observe how many traces goes here. Say let it be n1, and here let it be n2. Okay. So basically, right, what I do here is this part, or the numerator part, is nothing but the mean. Okay. So you are basically adding up those YQs. Those YQs means those traces for which, right, your input is constant. Okay. So you will see that I have used here two sigma notations, this one and this one. So this notation, for example, sigma, when I say q, tq equal to t, which means all those values for which tq is fixed to t. Okay. So here if I say q, like if I say, right, sigma q, xq equal to x, that means that all those inputs for which the input is fixed to x. Okay. So basically I am basically summing them up, and I am dividing them with the number of such values which essentially have that, which means I am calculating the mean in that case. Likewise, I am also calculating the other mean, which basically is essentially nothing but pretty much all the corresponding inputs. Okay. So basically you calculate, so you can easily observe that when I am randomly varying, right, then this set is expected to be kind of also containing some of these values of the other set. Okay. And then I basically calculate the difference of these two means, and then I divide it by the corresponding where like the variance is sigma 1 square, I divide in the denominator by sigma 1 square by n1 plus sigma 2 square by n2. Okay. So, now the idea is that, so this is your, so therefore, right, essentially if I simplify, then this is nothing but mu 1 minus mu 2 divided by square root of sigma 1 squared by n1 plus sigma 2 squared by n2. Okay. So, therefore, you can observe that if I like take lot of such cases, that means if I asymptotically vary this, then the TVLA essentially like will take a, if these two means are different, right, if these two means are different, then this will take a very large value. Okay. Therefore, if with large number of observations, the TVLA will probably get higher and higher. Whereas, if the two statistical distributions have got similar means, then essentially I expect to get a TVLA value which is close to 0. Okay. So, this therefore can be a measure of kind of understanding whether the means of two distributions are same or they are different. Okay. So, this again like borrows from statistical hypothesis testing, which means like you make a null hypothesis, and the null hypothesis is denoted as say H0. You make the null hypothesis say that the means of two things of the two distributions are same, and you make an alternate hypothesis, of course, which is say mu 1 is not equal to mu 2, and then you estimate this TVLA leakage. Okay. If the TVLA leakage is greater than a specific threshold, then with a specific confidence you accept this null hypothesis. I mean, if it is greater than the threshold, then you reject the null hypothesis, which means you kind of pretty much expect that the means are not the same. Okay. As you can see that if the mean is large, I mean if the TVLA is large, then you would expect that the means are not the same. Okay. So, this forms the basis of what is called as the test vector leakage assessment test, and essentially right is something that we will be studying in details in the next class. Okay. So, thank you for your attention.